Thank you all for coming today. This is the second in our science, what do we call Value in Science seminar series. We're just trying to get the word out on what we're doing in science group and the sort of work we do and the sort of things that we can offer to other parts of the organization. So today we've got a groundwater talk, and we've got Philippa Aitchison Earl to present to us today. Philippa has been with us for quite some for longer than some of the other people in this section.
Less than Ken.
But less than Ken. That's very good. No, she has been part of the section for a few years now, and is one of our senior scientists. And she's going to talk to you today about I think it's a good little story, a good little example of the sort of thing that we do. We collect lots of monitoring data, lots of long-term monitoring data, short-term monitoring data, and when we look at the data, sometimes we find things that are interesting. So this is an example of having a look at some of the data that we've collected over the years, finding something interesting, and investigating what it is it means, and what do we do with it. So, but before she gets into that, I better go through the safety thing. The exits. If there's an emergency, there's an exit here, and apparently there's an exit down at the other end through the other room. And we'll go through the exits and assemble out in the car park out in front of the building. There's toilets. There's men's toilets there. I'm not sure where the ladies' toilets.
Behind that bush.
Oh, right, behind the bush. Okay, well,
It's a really bad start.
And yeah, beyond that, I think there's not really much more to say. But, please welcome Philippa.
Right, bright red Philippa. Okay. Right, when I first was asked to do this talk, this is the original title of the presentation, which was Follow That Water Drop, an Adventure in the Groundwater System. Now, being a scientist, I've done the typical thing, and I found a more interesting piece of data, so I thought, I'll change it completely. So there's actually been a change for this. Because the pointer won't change the slides, can I get you to be my slide?
Do you need to hold that?
No, well, it won't change the slides, so we have to keep. I'm going to have to keep walking up and pushing space to change.
Sure.
So if I can get you to be
my
space person. Thank you. Okay, so I've changed my topic now to come on underground, be a groundwater scientist. So if we start off with the really simple stuff, what actually is groundwater? So on this example here, which is from one of my children's books, which is a really cool one actually, and this is Wally the worm digging down into the groundwater system. So we've got the land surface here, and then we've got the soil and stuff here, and the water will get through that soil, but this soil here and rock and sediment we call the unsaturated zone, because it's got some water in it, but it's also got some air in it. But then you eventually get down to here, and you can see that this is shown by lots of little gravel bits, which is just like Canterbury is. And when it's saturated, it means that every available extra space down there is filled up with water. So the difference between those two is this line here, which is called the water table. So if you go down to the beach and you dig a little hole and the water seeps into that hole, just like Wally's doing, you've hit the water table. When you're at the beach, it's quite close to the surface because the sea's so close. If you go further inland, like to Darfield or something, you might have to dig down 50 to 100 metres until you hit that water table. So that's it. Right. So it's hard to imagine the groundwater system because groundwater is underground, and that's why so many people apparently find it boring. I'm not sure why. So the only time you can see it is when it actually discharges back to the surface and springs. And yet globally, groundwater is 30% of all of the fresh water that's out there. A lot of it's locked up in glaciers and the like, and surface water is only 1%. So we think groundwater is pretty important. And often when you see a water cycle, it doesn't even have groundwater in it. So because you can't see it, a lot of our work we have to do by taking measurements of where we actually can get to groundwater. So that's wells which are drilled down into the ground or springs where it comes out. So basically it's like we've got a pin board of Canterbury, and we've got all of these little pins pointed into it where we've got wells that we can take measurements or take chemistry data, and then we have to interpolate what's happening between that. So it is seen as a bit of a black art because of that, and one of our sort of magic methods to look at that is but basically using a lot of fluid mechanics and the like. So it's all very complicated, it sounds, but basically we're taking pinpoints and trying to make something out of all of that. So one of the readings that we take is the depth to the water table, which is here. And to take a depth to the water table, I brought in one of our prodders, or a dipper, pretty good name. So this is what staff out at our Kaianga office use. We've got five staff out there who are doing the water level and chemistry measurements. And all we do is we go up to a well, and let's just pretend this here is my well, and we lower the prodder down it, and when it hits the water, and it's that easy. Sometimes you've got to wind down over 100 metres, so it can get a bit sore on the old hand. Okay. So our Kaianga staff, they've got about 350 wells they measure on a monthly basis, and they've also got over 100 wells that they've fitted automated recorders on. Can I get you to move me forward? So this is an example of a member of our section. It's only taken 3 years to turn them into this. This came to us nice and fresh and young. And yeah. Okay, so this is a well, and here's the casing going down into the ground, and this is product there. And he's measuring the water level there. And you can see some of these wells have got really complicated headworks to pump the water out and then to send it to irrigate around the property. So this particular well is in an area called the Perioral Valley, which is what I'm going to focus on. So if we zip to the next slide. Okay, so I'm going to pick some water levels that we've measured in the Perioral. So here's Timaru here, and the Perioral is about 10 kilometres south. So we've got the Perioral River, which has a north branch and a south branch, and they converge through a sort of gorge here. And the river flow is measured at a site called the Perioral at Hutt's site, and you're going to hear about that site a bit in the talk today. The river flows down through a river valley and down towards the coast here, and there's the township of Perioral there. Surrounding, so you've basically got a river valley, and surrounding it, you've got this sort of hummocky, loose downland. So if you've driven down south of Timaru, you know when you're at Timaru, and then when you're south of Timaru, there's lots of hills and the like, and then you drop down into these river valleys. So this is one of those little river valleys. It's not very wide, 2 to 3 to 4 k, say. It's really not very wide at all, but that's the system we're going to look at. So if we move to the next one, please, Carl. So here's some nice aerial photos of what the Perioral Valley looks like. So this is the Perioral township here. This is the Silver Fern Farms freezing works. You can see the beautiful discharge that they do to the coast, but that's not the subject of this talk. Here's the Perioral River running up through here. Now, for those of you that have driven south of Timaru, when you're coming along State Highway 1, you'll know you're on that hummocky downland, and then you drop down here into the river valley. You go down quite a big terrace. So this is the terrace here, which is really the extent of that valley system. And then on the south side, we've got the same sort of thing happening. We've got that rolling downlands coming up quite close to the river, so you've got this narrow river valley. Next one, please. This is another view of the Perioral taken from the south branch up at the top here. So here's the south branch here, and we'll meet up with the north branch, flow through the gorge here where the Hutt's recorder site somewhere in there, and then flows out to the sea. Next one. Okay, so we measure some groundwater levels currently at several sites, and we have measured some in the past too. So this is just, they're mainly in the lower part of the valley. So here's the township here in State Highway 1. All the sites that are shown in yellow are sites which are measuring shallow wells, which are measuring the water table that we looked at in the diagram of Wally the Worm earlier. So I'm just going to start off with a couple of sites here, which I'm going to call Brassel's Bridge, and you're going to see this term quite a bit. And this well here, which is at Pooks Road. So if we zoom to the next one. Right, these are the groundwater levels that have been measured at Brassel's Bridge since they first started in 1969. They've been measured monthly through to the current date. And if I just zoom to the next one. And this is the levels measured at Pooks Road, which has got an automatic recorder that measures at 15-minute intervals, and it was started measurement in the 1980s through to current date. Next slide. Right, so here they both are. Now this is where we're going to attempt to try and get interactive and get you guys to have a think about being a groundwater scientist. So just looking at them, would anybody like to hazard about anything they can see in that data? And you can't be wrong.
Declining.
Declining, okay. Can anyone see anything else?
There's a difference in the volume between the two, or depth between the two sites.
Yes, yep. So I get a room of scientists and you're going to pick up things that I didn't even think to talk about today.
Growing variations between highs and
Yeah. So there's some definite things happening in there. So when we've got sites like these, we've got this really long-term data. I just want to say this is what's so valuable to have long-term data, because if you picked a site like this one here and you only looked at the period of data just say through there, or just say through here, and the reason there's gaps there is that for some reason or other it was decided to stop measuring that well, and I started work there and it got picked up again. But so if you just looked at one piece of data in isolation, you don't always see these long-term trends. So these long-term sites are so valuable. So definitely I think that there is a declining trend. In this one here it's gone down by about maybe 60 to 70 centimetres over that period of record. And this one here, it's gone down by maybe up to a metre over the period of record. And as someone pointed out, it's still got a very large variation there, so it's still getting high events, but certainly the lows are getting lower. And you could probably even say at this site here that that rate has been speeding up. The rate that it's fallen has been speeding up in recent times. So if we zoom to the next slide, please, Carl. It's quite nice bossing your manager around. Okay, so the red arrows here is the two I showed you were here and here. We can see the same thing at these wells here. So it's happening all over the valley. Right, so if we could go to the next slide. Right, so this is, I'm going to try to get you to think like a scientist and help me come through for what is, come up with ideas about why that trend is actually happening. So to do this is how we follow things in the groundwater section, and I imagine most of the rest of environmental monitoring, where we follow what we call the scientific method. The first thing would be to ask a question. So the question for this is, well, what is causing a declining trend in the groundwater levels in the Perioral Valley? And then we try and do some background research. So rather than reinventing the wheel ourselves again, we look at any existing data that's there. Has anyone else looked at this before? What have they come up with? What else do we know about the system? And then we construct a hypothesis, and I put a series of hypotheses here too. Now if you think yourself back to science class at high school, where basically if you do a hypothesis, you're coming up with a statement which you then test. So in later slides I'm going to show some examples of a statement which you then test. So when I had to write these, I actually had to think quite hard to write hypotheses, because we don't really write them, but we're sort of thinking them in our head. We're like taking all the possible variables that would cause something and testing each one as we go along. So the test bit, analysing the data and coming up with some sort of conclusion, and the most important one for us is to actually be able to communicate what we found so it can actually be used. Right, so let's move to the next one. I'm going to give you some of the background research so that you can see what do we know already, and then we can test out all of those various different hypotheses. So next one along. So when you're talking about groundwater, one of the most important things is to actually look at the geology which the aquifer is within. So in this case here, here's the Perioral at Hutt site, which is up the top here, and this is a geological map taken from the Q map, which was produced for all of New Zealand by the GNS now. So in this upper part of the Perioral, we've got much older marine-based rocks, things like limestones and siltstones and the like. In fact, there's a whole lot of really cool karst holes by the time you get up there in the limestone, which are sinkholes. So in the top bit of the catchment, you've got that. The bit where the river, this white bit, is basically the recent river gravels that are part of the Perioral River system. So they're quite recently deposited within the last few thousands of years. And then you've got this light yellow bit, which is just slightly older river gravels, but still river gravels nonetheless. And then you've got this orangey bit, dark yellow bit, which is the loess-covered downlands. And loess is that very fine-grained silt which is actually blown onto the land. You see the same thing on Banks Peninsula, that sort of soil that you get there. Okay. Right, if we go through the next one. Now, actually, sorry, it's going to be a pain if I go back in the slide, just so I orientate people. Page out's on the far right at the top. Okay. I'm just going to show you a geological cross-section, and a cross-section, rather than looking at something flat on the surface, we're just going to cut a slice through the middle and have a look at what it looks like pretty much from the huts through to the coast. So next slide, thank you. Okay, so this is the huts end, and here's the coast end. So up at the huts we've got those older marine sediments that I was talking about. These lines here are wells which we've got, which we, as people drill the wells, they write down what they find on the way. So they'll say something like 0 to 5 metres gravel, 5 to 10 metres limestone, or whatever they find. So from that we can try and work out what sort of deposit they're in and how they relate to each other. Now what we're going to focus on is sort of this top 10 to 20 metres, which I've shaded in the light blue there, and that's those shallow river gravels which are associated with the recent deposition of the Perioral River. Underlying them there is another gravel formation. Just to speed up the presentation today, I'm just going to give you some background information that although that may be linked to the shallow stuff in the long term, it's not in the short term, so we're just going to pretend it doesn't exist for today's presentation. So if we zoom on. Okay, and the other thing that we already know about this system is that the groundwater levels and river flows are incredibly related. So what I've shown here in the red is the flow which is recorded at the Perioral River at the hut site, which was the top of the catchment, and in the blue are the groundwater levels in our well that we've got at Pooks Road. So when you get a river flow event coming up, your groundwater level comes up too, and there's a time delay in that. It might only be a couple of days, or it could be up to a week. It sort of depends on how empty the groundwater system is at the time, but very, very, very related through time. So we know that about the system. So next slide. Okay, so another bit of background information to think about when you're trying to test what's happening is thinking about the water cycle. So this is a very basic one. We've got rainfall called precipitation falling on the ground, some of that becoming runoff to our surface water bodies, and some of it infiltrating through the ground to become what we call groundwater recharge. Here's that water table we looked at before, flowing through the aquifer, discharging from the aquifer, maybe back to a stream or maybe to the coast, and then becoming part of the cycle again as it's evaporated away. So it's a nice pictorial way of looking at it. Next slide, please. If we look at it in a sort of more mathematical, scientific way, this is sort of like a black box approach, where this black box is a bit of groundwater. And we can think about the inflows and the outflows that we have from that groundwater, which is something that we call a water balance. So the sort of inflows we've got is the rainfall falling, we've got evapotranspiration coming out, we've got pumping coming out from people taking from the groundwater, we've got stream flow, which may be interacting in several ways. I'll come to that a bit more later, but it may be stream flow sourced from the groundwater or stream flow that's seeping back into the groundwater. We've got this recharge moving down towards the water table. We might have interaction with deeper aquifers. And obviously the outflow and inflow. And in the middle of this box is shown the water table here. And that water table will move up or down depending on the balance of all of these other parts of the system. So, looking at this diagram, which sort of gives you an idea of inputs and outputs, I'm going to go up to the whiteboard for a bit and see, thinking about that groundwater level decline that we observed, would anyone like to hazard any guess about some of the things that we could test to see if they are causing that decline, using this as a help? Not from my own section, unless nobody else can say anything.
Stream flow.
Stream flow, right. So stream flow doing what, do you think? Right, so I'm going to put here, because we're thinking of water balance here. So inputs, which we call recharge. And at the other end of the system, we've got the outputs, which we call discharge. So, stream flow, I've got different colours I do. Stream flow, and we're going to have a nice slide of this later, but stream flow can actually be both. So I'm going to put it in both. Any other ideas?
Pressure.
Sorry?
Pressure?
Pressure.
As in, like, pressure of spring flow, water flow out of artesian water flow. I
can't think how I phrase that. this particular system, and this is because of the, I haven't given you a full background of it, but this particular system, we're dealing with a water table, which isn't under pressure like an artesian system would be. Basically, it's like if you've got a bucket of sand and then you pour some water in it, and the water level that it'll be will fluctuate up and down easily without, it's not under pressure, it's just what's there, really. So nice idea if it was in a different system, but not really for this one.
Rainfall variability.
Rainfall, yep. So that's another inflow. Can you think of any other ins that might come into the system? I think we've pretty much got them all there at the moment. How about some outs?
Abstraction.
Abstraction, thank you. Okay. So if we could...
Evapotranspiration.
EBT. So that's sort of rainfall EBT. It's sort of like an output, but I'm just going to group it with rainfall for now.
How about irrigation, isn't it?
Yep, that's part of abstraction. So it can be abstraction for, but
irrigation coming back into the system?
Yeah. So EBT. So I've got a future slide coming up where we talk about land surface recharge, and that's the water that gets through to the groundwater from a combination of rainfall and of irrigation. So yeah. Okay. I think you've got pretty much the ones I've got stuff to cover. You can mention them more and I won't know what to say. Okay, so what we do then for the scientific method is we look at each of those, and let's say I went in with a preconceived notion of what I think was causing something, and often in Canterbury we always think about abstraction. So let's say I went in with that preconceived notion and I only looked at abstraction. That wouldn't be scientific because I haven't ruled out everything else. So even if you're pretty sure you know what something is, you still need to go in and make sure that you have ticked off all of those other boxes to prove that it isn't one of the other things. Okay, so if we move to the next slide. So let's have a go at the first one. So this is the land surface recharge. So I'm not going to bother reading each of these individual hypotheses because I actually had a lot of trouble trying to write them to sound any good. But basically our first test is it recharge, land surface recharge? So move to the next slide, please. Okay, so what is land surface recharge? It's that combination of rainfall falling at the surface and irrigation water falling at the surface that makes its way through the soil profile and actually gets down to the groundwater. So we've got two ways of trying to measure that. The first, we do direct measurement using something called a lysimeter, and I'm going to show you a picture of that in a moment. We've got 4 lysimeter sites as part of a network, which is part of a national network. But as you can imagine, with all of Canterbury, and we've got 4 sites, well, we obviously can't measure it everywhere, so we use those measurements to validate models, and then we have to use the models to try and look at these things. And the models use things like soil types, rainfall, and irrigation practice. So if we move to the next slide. This is a nice picture of a lysimeter site being set up. It's actually from the North Island, but I'll put it in because it's quite a nice picture. So this is a lysimeter, and it's basically a barrel that's just being driven over a soil column where they've tried to keep the soil column inside as intact and natural as possible. So any rainfall irrigation water falling on that, or that infiltrates its way through the soil profile, will be measured by some sort of measurement like a tipping bucket or the like, and they'll have instrumentation set up here. So obviously they're going to backfill the site back up to the ground level, and you can see that they've got several lysimeters here, and that's because if you only have one and it happened that you had an irrigator that went over it that didn't have a very even application, you might end up with either under measuring or over measuring. So the more sites you have, the more you can average out and get a more realistic result. So if we move to the next slide, this is an example of one of the models that we use instead, because we obviously can't measure it directly everywhere. And this is a model, just a very simple daily soil moisture balance model, and it's one that's set up within a Fortran code by one of our previous staff members, David Scott. So what it does is it takes on a daily basis how many millimetres of rainfall fell, how much irrigation water was put on, and then it takes off daily EBT. The model can account for runoff, but we won't worry about that at the moment. And it feeds those figures into a soil column. In the soil column, we get the data from our soils layer on the GIS system, which give you a water holding capacity as a depth in millimetres. So if you've got a light soil or a heavy soil. So if you've got a heavy soil, you might have a water holding capacity of about 150 millimetres. So in that case, that would be 0 to 150 millimetres, and on a daily basis it would keep either filling up or going down, depending on how that daily balance of EBT and rainfall went. Once that's full, any extra water that comes on is allowed to drain through to recharge. So when we talk about irrigation water being added, we're not saying that people are inefficient irrigators, because when they irrigate, that water doesn't directly go down to groundwater, because that wastes them money too. But what it does is it keeps that soil profile wetter, and when there is a big rainfall event, it's much more likely that that rainfall will keep travelling down to recharge, because it doesn't have to fill that soil profile up. So we tend to see more recharge under irrigated land than we do under dry land. So if we go to the next slide, here's some data from the Perioral Valley. So if we push the button again. So using that model, we can come out with monthly outputs of what dry land surface recharge would be. And there it is in millimetres over here. And you can see over time there's a very slight downward trend. And the same thing but if we count for the fact that the irrigated land area has gone up over time, it's actually a very slight upward trend. If we push the button again, please, Carl. So there's our groundwater water level decline. Do you think changes in land surface recharge are driving that? Anyone? No, I would agree, no. So that downward we're seeing here, this doesn't really help explain that. So right, move on to the next thing. What else could it be? So let's look at the recharge from rivers and zoom again. So rivers interact with groundwater in two ways. We can have what we call a losing river or a gaining river. So with a losing river, the level of the river, which is often called the stage, the level of the river, if it's higher than the surrounding water table, groundwater likes to flow downhill. So water will be lost out of the river towards the groundwater system. And that's what you see in the inland rivers of Canterbury, like the Selwyn, the Ashley, where they're losing their water to groundwater. In fact, they often go dry in their middle reaches. At the other end of the system, we have the water table is higher than the river. So again, the water wants to flow downhill, down gradient, in a more scientific way, towards the river. And in this case, we get a gaining stream. So the stream flow increases as you go along the river. And this is what we see in the coastal ends of the Canterbury system. So that's why you see the Selwyn River flowing on the top end, dry in the middle, and then flowing again at the coast. At the coast, it's actually picking up water from the groundwater system. And this is exactly what's happening in the Perioral River. Hang on, I'll find diagram. If you push the next button, please, Carl. Okay, so this is a flow profile of the Perioral River, and all this data is thanks to the surface water section. So here we've got flow measured in litres a second, and here we have the hut site at the top of the catchment down to the coast, and State Highway 1 is located about here. I've just shown you a couple of average flow profiles for mean flow and for mouth, which is just a measure of a low flow. So at mean flow, in this breach here, the flow is going down, so it's losing to the groundwater. The same thing happens at a low flow. And in fact, the amount that's lost, you can see, is about the same, whether you're at a mean flow or a low flow. And the reason for that in this system is that you're only looking at maybe 10 to 20 metres thick of gravel, so once they're full, they can't take any more water. So it doesn't matter how big a river flow you've got, it's not going to fill up the groundwater anymore. So the river loses to groundwater at a consistent rate. In the middle reach, the river can often be dry, just like you see in the Selwyn. And then in the tail reach, it picks up from groundwater again, so it becomes groundwater fed. So if we zoom to the next slide. So knowing that the river interacts with river flow so much, and we've seen from the earlier slide how the groundwater levels correspond, I asked the hydrologist to have a look at the data for me for the Perioral huts to see if it's changed. So it's been measured since the early 80s. Here's the blue line is monthly mean flow, and the red line is a 7-day annual low flow, and from what I understand, how they've explained it to me, is it's just taking the 7 consecutive days of every year and giving you the 7 consecutive lowest flows of each year. So mean flow doesn't really look like it's changed a terrible amount, and the 7-day annual low flow, although it's bounced around, there's no overall trend to that data. So if we push the button again, there's our groundwater level decline. So do we think this is causing it? So the volume of water that's coming in hasn't really changed. Right, so next thing, let's look at the other side, the outputs. So let's have a look at what's happened with abstraction. Water. Got to make sure I don't eat the one that I put the fodder in. Because who knows what's down those wells. One of our team members found a dead hedgehog recently. Okay, so next slide. Right, this is looking at groundwater abstraction, people taking from the shallow groundwater by the river valley. Now, I've got the graph here from 1990 up to 2014. It's harder to get the data before 1990 because the consents database doesn't hold it particularly well. It's quite hard to get. But I can tell you that they pretty much started irrigation in the late 1960s within that valley, so it would have been ramping up from the 60s, from zero to that figure. So you can see that there was increasing irrigation, and I'm showing this as consented irrigated area rather than a volume, just because that's a figure that's easier to compare with the consents database. And then since about the turn of the century, it's stayed pretty much static. So if we put the next, so again, there's our groundwater level decline. Now you could say, well, maybe if abstraction was going up through that period, so here's about 2000 here, that maybe that might be able to explain some of that decline there. But given that it's been static since about here, can it explain that? So yeah, again, it's not looking like a clear candidate. So the next one. Okay, so the other discharge we could look at is the discharge to stream flow, where the groundwater, those gaining reaches where the groundwater is feeding back into the surface water. The next slide. Okay, so the flow at State Highway 1 and the Perioral Rubber has only been measured since 2008. So it's really hard to tell anything when you've only got 5 or 6 years of data. So what I've shown you here is the State Highway 1 site is in blue and the Hut site is in green. So you can see that the State Highway 1 site has much lower flows at times of the year than the Hut site has, but with only so few years of data, it's pretty hard to make a conclusion about that. My understanding of this system would be that it's driven more by changes in recharge, being the river flow, because we see our groundwater levels going up after the river flow increases. So I think that the discharge from groundwater back to the river is more likely to be changes in that, and more likely to be a consequence of change in groundwater level decline rather than actually the driver of that decline. I don't know if I've explained that very well, but yeah, I think this is less likely anyway. Next slide. Okay, so we've looked at the things in that volumetric water balance and got a bit stumped. So I was a bit stumped too, and I know Nikki, who I was doing this project with too, were a bit stumped at what was actually causing it. So I started trying to think about some other external factors, and sadly one Friday night when I was watching 7 Days, I started thinking about gravel in the riverbed, because there's a catchment just south of us called the Otaio, where the users there had told me that the gravel had been building up and that was affecting their river flows. And I started thinking, well, what would happen if you did the opposite? So all full of enthusiasm on a Friday night at 10:30, I accessed some online ECAN reports. See, Ken, I work hard. I accessed some ECAN reports online about the riverbed from River Engineering, and I had a bit of a eureka moment. They're quite exciting, the scientists. Okay, so next slide. Okay, now you've seen this one before where we're looking at the losing gaining reaches, but again, imagine you've got this riverbed here that's losing water to the groundwater. How much is lost is driven by the difference between this and this. And so if you change this level, the level of the stream, and moved it down, you're also going to move that groundwater level down. So if we move on. Now, luckily for us, the engineering section has undertaken Fairway, which is basically the active river channel, bed cross sections at 600 metre intervals, which are shown by these red lines. So here's the coast, and that's not quite up to the huts because they've joined the thing here, but up the catchment. So here's the Brussels Bridge, Hooks Road, State Highway 1. So all these little red lines are at 600 metre intervals up there, and they've done them in 1949, 67, 86, 99, 2009 and 2013. And the reason they've done them is because they've got an active flood control work scheme. But there was a big massive flood in this river in the mid-1980s. So from these surveys I could get the bed level, and I decided to use so that's the base of the river. So I decided to use that as sort of an indicator of what the river height would be. So if we zoom to the next one. Right, so those three sites that I showed you earlier, being Brussels Bridge, Pooks Road and State Highway 1, this is just picking three of these cross sections to show you how they've changed between 1949 and today. So this is a zero line here, so if you go above that line it means that you've gone up, as in gravel's built up and you've degraded. If you go below this line it means that the gravel's been moved away and you've been degraded. So from 1949, the Brussels Bridge site, it went up a bit and then it's gone down and it's currently about 20 centimetres lower than it was in 49. If you look at Pooks Road, it's been going down the whole time and it's now about 1.3 metres lower than it used to be. And State Highway 1 went down, it's come up again slightly recently and is sitting about 60 centimetres lower than it used to be. We go to the, hold on, wait a second. I'll get on to that in a second. Okay, so reading those online reports and talking to the river engineers, they've concluded that it's gravel abstraction, which has accounted for about 40% of the degradation, which, sorry, I do need to go back a slide, which has been about 40% of the degradation over this period, sort of 60s through to the 80s, and about 90% of it through this more recent period here. So it's people taking the gravel from the rivers using diggers that have caused this change. Push the button again. Okay, so this is taking the same data but showing you over the entire profile of the river from the hut site through to the coast here. So each of these locations is one of their 600 metre survey points. So again, here's the 0 point. So if it's gone above that, it means it's graded. Fallen below that, it means it's degraded. Here's where our Brussels Bridge, Pooks Road and State Highway 1 sites are. So although we've got one site that's gone up, all of the rest of them have gone down. And I've shown you a different time series here, 67 to 2013, because that's the period that we also have groundwater level measurements. We don't have groundwater level measurements back to the 40s. So you're looking at changes of sort of 80 centimetres, getting up towards a metre. Quite significant. All of that volume has been moved away in that time period. Okay, next one. Right, so what have the groundwater levels been compared to that? If we take this first one here, this is the first well that I showed you, which has been measured since 1969, and if we compared the groundwater level decline over that similar period, there's around about 60 centimetres compared to the riverbed degradation there. The next site, which is the Pooks Road, here we go, it's had about 1 metre decline, similar to what the riverbed has degraded in the last one. The State Highway 1 site is sitting around about 50 centimetres decline. Water. So the similarity between this riverbed level decline and the groundwater level decline would make me think that this is probably the main driver of the groundwater level decline, because we can't see any other clear factors within those other things within the water balance. What do you think? Can I convince you? Okay, so we did check out this using some groundwater modelling that one of my colleagues, Fuad, undertook, which did show that if you lowered a riverbed, you would get a groundwater level decline. And it interestingly also showed that perhaps you might actually get an increase in discharge from groundwater back to surface flow in the coastal reaches. But that's not something that we can test with only like 5 or 6 years of surface flow data. But it's an interesting thing to look at. So next slide. And there's a digger working in a riverbed taking gravel. So if we move on again. So if we went back to that scientific method from the start, we had our question, we had our hypothesis, and then we had the results, which I think that the main driver of that decline is probably this riverbed degradation, because I can't explain it with other factors within the groundwater balance. So that's the thing with groundwater sites, that there can be lots of factors playing in to give you a result, and sometimes you can't rule out a factor, but you can suggest more likely factors. So if we move on again. So what does this mean? Well, the first thing would be that you're going to reduce groundwater storage. So if we imagine this box again here, and we've got this river and we've got this groundwater system, you push the button again, Carl, and then suddenly we move it down to here, and we drop our water table down to here, and button again. That means that where we used to have a groundwater system this thick, we've suddenly got a groundwater system this thick, so we have reduced that storage. So that could be anywhere between about 3 and 13% I've estimated. Interestingly, some of the shallow groundwater users within that valley have said that they've had more difficulties with pumping in recent years because their water table's fallen, and they've blamed that on a dairy conversion inland of them. But I would think it's more likely to be this riverbed degradation rather than the dairy conversion. And of course, changing how things interact can change other things like perhaps the groundwater discharge towards the stream at the coast. So if we zoom on again. So internationally, this is also seen. There's lowered water tables and a lack of aquifer storage because of sediment mining has been seen in California, Italy, Spain, France and Poland, so it's not just something that we've identified unique here. It's an issue that we haven't really looked at in the past for the management of sediment in rivers. So I've talked to river engineering and presents just to say, well, we have noticed this. And so this is one of the things with science, is that we collect this data, we find something, and it was something that I didn't expect, I never even thought of it. And, but then we have to decide where it goes to from there, and that's getting out of our realm and into the realm of planners and facilitators and the like, because who would decide the relative value of keeping up the flood carrying capacity, which is why they dig the gravel out of that river to stop a big massive flood again like in the 80s, versus the fact that the water resource is going down. And I think we should also think for this valley, the people who are using this water resource to actually irrigate from are the same people who would be affected by flooding. So yeah, who makes that call? So next slide. Right, and I'm just finishing up with one of my favourite slides from my children's book, which was imagine Deanna's surprise that she wasn't percolating. Okay, so yeah, I think it would be quite interesting if we could sort of talk about that sort of values-based, when we find something and where it goes to. Yeah. Any questions?
Any questions? Yep.
Yeah. Did you consider other factors like more efficient irrigation, and maybe a causal thing, or perhaps climate change with less precipitation, more EBT?
Yeah, well, the climate change stuff would have been picked up by the land surface recharge modelling, which takes data from NEWA's virtual climate network, and so it's using actual values of rainfall and EBT over time. So if they had been changed, that land surface recharge plot over time, I showed you that had that very slight decrease in trend. But then if you added in the extra irrigated area, it would actually have a slight increase in trend. So no, I haven't specifically considered climate change, but that's getting out of my area of expertise, but I relied on NEWA's data to hopefully properly encompass that.
And more efficient irrigation, could that
Well, if people are becoming more efficient at irrigation, they would perhaps use less water, but it would also mean that we'd get less groundwater recharge. When we run our models, when we try, like that model of David Scott's that I showed you with the daily soil moisture balance, it makes an assumption that people are 80% efficient at irrigation, and so that's an aspirational target that people are working towards. So it doesn't encompass changes like that. But if a whole up to a metre change in groundwater level is quite significant, and just from my experience, I find it difficult to think that factors like that might have a small effect, but I can't see them having such a large effect as that. It's just the vibe. Sorry. Yes.
I was thinking about your values question, I suppose, at the end, and well, it was maybe this does relate to that, but I guess it was the so what sort of question. It said, is that decline in groundwater level actually causing a reliability problem for abstractors?
Yeah. Well,
does it matter?
Yeah, that's the whole thing. Now, this piece of work is part of a piece of work that Nikki Wilson and I have been doing, which is still going, hasn't even hit external review yet. And so when it's through that process, that sort of question could go back to the community, perhaps as maybe part of the sub-regional planning. I don't know. This is getting, again, as scientists, we can find. We can discover something and we can alert people to it, and yeah.
Okay.
You can probably answer that better yourself, Ken, than I did.
No, it's fine.
What about more efficient land drainage? As technology and like farm machinery and tile drain efficiency has increased?
They don't really have any drainage in the Perioral Valley, do they, Nikki? Not that I know of. It's it isn't like coastal. These South Canterbury catchments are quite steep topographically, and so you don't have like you do around Ellesmere, where you're quite flat and the water table's really close to the surface.
Presumably, you could test your hypothesis a bit more by looking at some wells further away from the river, because they were all really close, weren't they?
I've got, we are limited to the data that we've got in terms of, I'll just go back a few slides to find, so it's going to be right, sorry, add animations and things longer.
I suppose what I'm really asking is, I presume you would expect to see further away from the river a dampening down of that difference. Would that be right?
Because probably would be, yes. These sites are all of the sites where we have data. The reason that I can only identify a decline within these sites are because they're the only sites that have got a record long enough to see anything. Some of these other sites might only have 10 years of record and they might have stopped 30 years ago. Others of these sites out here, they don't actually really get their recharge from the river, they get it sort of from this direction. So I'm limited by the data that I've got. Yeah. But that probably is maybe something that could be modelled, Fuad.
I think those will show that.
It does show that within your model across, right, well there we go. I haven't included Fuad's modelling results within that because we thought it was just getting a bit too long and perhaps too complicated but yeah. Sorry, is your question?
Do you think there's any effect from localised well experience on those readings, given that those, I think a lot of those pools are actually productive wells?
Yeah. This well here where we've got the 15-minute data on, there's about a 4 centimetre effect on that well from pumping from a nearby waterhole. When you're in a water table aquifer like this, the interference effects, it's what we call an unconfined aquifer, and the interference effects don't spread out very far. When I've done aquifer tests within this valley, I've measured wells at 100 metres away and I've measured nothing. You've sort of got to, you've had to be quite close to see something, and so you'll get localised interference in the short term, but when they stop pumping, that comes back to normal, and you wouldn't expect to see a long-term 1 metre decline. The thing about this system too is from, I'm going to remember where some of these slides are. If we go to that one about the water levels over time, where did I put that? Stuff we know. Okay. When you get a river flow event, that groundwater level pops up again really quickly. So it's very, very responsive to changes in recharge. When the river flow declines, your groundwater, it's like your ground. They're quite again. Because they're so steep topographically, these catchments, you take away your source of input. It just all drains away under gravity. So. I lost my track a bit there. If you've got something like interference or light, it just gets swamped out the minute you get a change in the recharge coming in. It's the dominant factor for this particular system.
Is there a question there?
It's not really about groundwater, but it's more about the flooding of the river prior to getting the representative evidence of it flooding the river.
I don't know, I'm sorry. All the river engineering people have another meeting, which is why none of them are here, because it would have been nice to have one of them here, because I have talked to them about this. I know I think it was 86 it had a big flood. I don't know what it had before that. Does anyone from Surface Water like to hazard a guess?
I know that 86 was the big one.
Yeah. Yeah.
And our record goes to 79, isn't it?
82 is the hut
So,
site.
yeah.
Yeah. You might have
I mean,
gauges.
but there is across the South Island, we see changes in flood frequency which are linked into global atmospheric changes. So on a cycle, and I'm just trying to think what cycle we're in now. We're in a more flooding period. There was a period from the mid 90s through to the mid 2000s where there were hardly any floods on the east coast. So there have been changes in flood. But having said that, what Philippa was saying is that it doesn't make any difference for recharge whether the river's in flood or low. It's still recharging at the same amount. So
It's like again, you've got a bucket of sand that's only so big. So you take that bucket of sand and you pour 2 cups of water in, or 3 cups of water and it's full. You pour your 4th cup of water, it won't go in, it will flow out. And when it flows out, it basically just stays in the river. So you can't force any more water into something that has no more room.
I guess if you take half the sand out of the bucket, then it flows earlier.
Yeah. Well, that's probably why you get more discharge. According to the modelling, would say that perhaps we get more discharge out of the tail end. So I meant to say too that we haven't looked anywhere else in Canterbury, but I have a feeling the same thing happened in the Waiho River because our data was going down there until about 2004 before an irrigation scheme extended there. We've got another well by the Waihi River that's got a downwards trend. Maybe that's the same here, and one of the other guys thought that maybe the Ashley River might have vagrant, so it might be other places too. We just haven't. We've only just found it. So, yeah.
So do you know how much gravel's actually being extracted? Because I've just done a trip around the districts to talk about hazards and things, and one of the things that's come up with them is some of them say that they seem to be getting a lot more gravel coming down the rivers, and so when flood happens, they get a lot more rubbish coming out the rivers.
Sorry, I'm a groundwater scientist. I don't. Yeah, if someone from River Engineering was here, that would be great to answer that. I know that they have red zones for gravel management, so they do try to not target areas that are really, really degraded, but I don't know where they are.
But again, on that flood, the fact that there was this sort of 10-year period without many floods did choke off a lot of gravel.
Yeah.
And you do see it in the river mouths where they had a period of starvation really, and now they are starting to get more gravel coming through again. So, and the trouble with people's memory is it's hard to think beyond about 20 years at the most.
Which is why long-term data is so amazing. The fact that we've got gravel levels going back to the 70s is great. But according to the gravel management reports, which are ECAN reports that I read, they were saying that 90% of the degradation was because of extraction for digging gravel out, not because of natural processes. For this catchment, not that elsewhere.
The thought that I've had is around alpine fault earthquakes causing rubbish to get into the rivers through landslides, and it takes about 200 years on this side for the sand to get to the coast. The gravel takes longer, and it's 300 years since the last one. So it's possible that there's a different amount, a slug of gravel coming down.
Yeah.
I mean, it sounds like you're saying that the gravel extraction is actually mitigating that.
I'm just parroting what I read on the River Engineering report. I wouldn't like to take any ownership of that.
but I mean,
Interestingly, Marion, sorry, I actually, when I was at university, I did on a field trip with Perioral, I actually did sediment size sampling. Maybe I should go back and do it again. Sorry, Tim.
Well, I was just going to say, I wondered on your graph that showed decline, there was sort of two, it was going down and then went up with distance. A bit the same thing, whether there was a slug of gravel coming down. They do that, you see a slug that make its way down.
If you've got the data, you can do it, but I've got some river surveys at certain years, and that's all I've got to compare it to.
Yeah.
So, so I mean, you could probably say if you're just there, there's nothing happening there, and it's mostly here and somewhere in the middle of there. So when it was.
So Philippa, you said you've talked to the river engineers about this. have you talked to other people? I mean, say you find this and you wonder, is it an issue? Who do you talk to? How do you find
Well,
out?
that's I'd like to know, section manager, because I've told my acting section manager. I've talked to the consent staff who deal with gravel bed zones, and I've talked to the river engineers. The river engineers have basically said, although they're not uninterested, but their prime focus is on flood carrying capacity. So as long as they maintain flood carrying capacity, they don't really care what else happens. So they're not saying they don't care, but that's their prime focus. And so they were saying to me, it's quite interesting that, this sort of thing about groundwater level decline might be picked up in the sub-regional planning process for the OOP zone, which is coming up soon. And so maybe someone might make some values judgment as part of that and say, we want groundwater levels higher. But on the same track, apparently they have river liaison committees. And again, I'm only parroting what I've been told here, so there's higher management than me that will explain it better. So they've got these river liaison committees who are dealing with the flood thing. And both of those are staffed by members of the community. So you want them in a way to be saying the same thing. And looking, you don't want one group saying, raise this, and the other group saying, but flood carrying capacity. So I'm raising this as, we find these issues, and then it's up to the people who deal with this sort of stuff. Be keen to, what do you do with it? I don't know, Ken?
I think that this is exactly the kind of debate that will end up in zone committees.
Right.
But that's why I asked that question about whether there was whether a value was being affected by the fact that there was less water in the groundwater system. In the sense, reliability was being affected, for example.
We've got one anecdotal account of reliability.
Yeah.
I would like to see, rather than, I don't want to ring up the community at the moment and say this until it's been through its full review process, and then this is an area that Nikki deals with, and she might want to think about how she communicates it to the committee. Just to pass the buck on that one. Yeah. That's something quite hard as a scientist. You don't know the formal, to be honest, I don't know the formal process you sometimes go through when you run, so that could perhaps be made clearer for us as an organisation.
As part of your international research related to the same trends, they discussing changes related to resource management?
There's a really good summary. I'm somewhat limited by what I can read by, as you've heard me complaining, Carl, about access to journal articles because you have to pay for them. But I have found a really good summary one about gravel bed management internationally, and they've got a lovely table. I can send it to you if you're interested. And they've got a lovely table of all of the countries and all of the types of things that have happened as a consequence of mining of sediment. And then they talk about ways that you could manage this better. So there's literature out there on it. Yeah, but again, that's getting outside of my area of expertise, which is very narrowly groundwater. So yeah, if you'd like it, just send me an email and I'll forward it to you. Sorry, I'm not officially supposed to get it.
To what extent do you think this is just confined to the sort of ground carrying rivers? I'm actually thinking about Christchurch City, the Avon, the Heathcote, the lateral spread and the rubbish that's gotten in the river through the quakes, and whether there have been some changes in groundwater near the rivers, which doesn't just affect, it's not just the channel capacity, it also then means you can't get as much infiltration, you get more overland flooding. Do you think that, in the more sort of silty rivers you're going to get this too? Or?
Well, might have to get some other people to jump in on this one too, but this is a river where you've got the flow on it is driving the groundwater system. The Christchurch Springfed streams are the output of the system, they're not the driver. So it's the groundwater level controlling the river flow rather than the other way around. So in terms of if you incised your channel further inland, you might get more inflow into it, but
Well,
on
a local scale, it might not work that way all the way down the Avon. I think it's quite possible that if you got some stretches of the Avon where the groundwater levels are higher adjacent to the river,
it could discharge.
Yeah, I mean it's the same principle.
Yeah.
Just minor
because
steps.
the ground's actually drops, and so it's the water's closer to the surface as well. So
Well, some of the young people was the Avon in the head are basically fed because the water table intersects the river bed. It's not because you don't get artesian springs till you further down. So if you lower your topographic, your land surface, you get more exposure to the water table.